We're live. Good morning, everybody. We were just waiting for some attendees to log on this morning. So good evening or good morning. I hope everybody's having a good day or is going to have a good day, just like we are this morning. Any problems with the audio? Can everybody hear and see us? If somebody gives me a thumbs up in the chat, that would be great, just to make sure. Anybody? Bob? Kale? Hi, Kale. Oh, there we go. Excellent. Thank you very, very much. And away we go. So just a couple of housekeeping points for today. If you can make sure that you still have access to the SharePoint that we had emailed out to everybody on Tuesday. The reason for that is that we have put the interactive PDFs of the day 2 build in a folder called day 2 already. We said we would do that on Tuesday to let you get access to them ahead of time. So please, we're going to have a little bit of a presentation and a talk about some tips and tricks. Then we're going to let you build a section of the robot or start to build a section of the robot. Then we'll go back and give you some more tips and tricks. We'll let you then build a section of the robot and we'll do that again. So if you do not have access to that, don't worry right now, just send us a note in the chat. And when we get a little bit of a break here or one of us isn't talking, we'll go and give you access, okay, so that you can see that. But you will need those today because, like I said, the format today will follow much like it did for the latter part of Tuesday. We're going to give you the interactive CAD files, talk about the build, and then give you some time to build and then work with us, okay? As I did say on Tuesday, our overall concern is that you don't get the exact robot built right now. There's a couple of reasons for that. We're going to use a couple of extra parts you may or may not have. A lot of you, I know have them. And that's just the way that we did our design intent on this one, because as we build these robots, we're trying to prepare for the future and look at what we think would be in a collection or not used in a collection. The big concern here is that when we start programming the robot, we're going to use both a servo motor and a DC motor to drive a portion of the lift and the object management system. So if you can at least build something that drives a servo and moves and another DC motor separate from the 3 DC motors on the drive mechanism for this robot, then you will at least be able to go through with us when James is coding it. And see how those robots move and do a couple of things. So, use your own initiative on this. I know that we saw a couple of pictures from robots on Tuesday, and some people are building different robots, and that's great. The idea here is to get you into that thought process and into the design process going forward. Right? There are a couple of housekeeping points we'll bring up for next week as well. Probably on Tuesday when we talk about doing the wiring and show you the electrical schematic for this robot, we're going to talk a little bit and get you prepared for programming so that you don't have to do it. But we will verify your software installation with you and that you are running the correct version of the software, okay? Because we're coding for a certain version. We're coding for the 2020 version. We've had a lot of people in the last couple of weeks who've downloaded the 2019 version or the new 2021 version, which are for different robotics competitions, not for what we're doing. So we just want to make sure that everything is correct because your libraries won't match up when you're going to work through it. Okay. So that said, I'm going to do a share screen here, and I'm going to get started with some wonderful tips and tricks for you. All right. So today we are looking at the elevator and the object management system, or OMS, as we call it. We are recording this and we will be editing the recording because we don't want to record the blank spots where you're building. And then we'll post those up to the Studica Robotics YouTube channel for your reference. You can also use that because our previous recordings are on there. So when we're talking about certain things with the elevator, as an example, we did do a session back in February where we built a simple elevator mechanism and programmed an elevator mechanism. So there's a lot of good tips and tricks in that session that will benefit you going forward as you work, okay? All right. There is a question in the chat about this, and I can't answer your question because this depends upon the competition. Okay, so when you get a competition document for Shanghai, the rules will be set out. All right. All I can tell you is that everything that you need for Shanghai and that you will be allowed to use in Shanghai will be provided to you in Shanghai. And those rules will come out when the competition document, the CID document, is released. Okay. So we can't tell you what you're going to need in the future until that competition document is released. All right. Okay, so we'll just continue on. So the elevator and the OMS, or the object management system, we are going to use both types of linear mechanisms that are in the system right now. All right. And linear movement is necessary in all types of robotics and automation. So anything from a simple 3D printer, which has a slide system and a belt, okay, with a threaded rod, uses the same type of mechanism as does a complex high precision staged industrial automation equipment. So the skill set that we're using here and teaching here can be used over all sorts of automation principles. Okay? The idea behind these linear mechanisms, of course, is that you're going to try to move something in a straight line. Right? So generally, the mechanism itself has one degree of freedom. Right? So to constrain that 1 degree of freedom, we usually accomplish this with either a linear guide or slide, a linear bushing or bearing system. Okay, and if you don't, you cannot constrain the actuator to control the movement in one direction, right? And there's other types of things you could use for linear movement as well. There's linear actuators as an example that we are looking at for the future, and a few other design systems. In your World Skills collection, there's 2 common linear systems that you can use with that. Okay, there's the miniature ball linear guide system, which I will show you in a minute. Okay, and there is the rack and pinion linear system, which I will also show you and explain to you just so that you can see it. Right. Okay, the linear guide system itself, it's a sturdy, very reliable, smooth system because it's got ball bearings inside the linear guides. These are able to withstand a significant amount of load with little flex because they're strong. We use a low profile linear slide system that has the M3 mounting system, okay? And, you know, to mount it, you can see there's a bit of a challenge there. They do line up, and we'll talk about that when we mount them and see them as they're going forward. Some teams we've seen have 3D printed an insert that goes between the slide and any extrusion piece that goes there, okay, so that they can mount parts quicker going forward as they walk through it. Okay, I'm going to stop my share, or can we go to camera 4? All right, and I'm going to make sure I don't get yelled at today, so I'm going to lean real forward here on camera 4. Okay, so we do have our linear slide system. This linear slide system is mounted on one of the low profile channels, okay, that's in the collection, and it's mounted on the sides. All right. So that's your linear slide system. So there's a guide block that mounts through here. Please note that there's 2 stops that are on the end. So there is a stop right here, okay, a hard stop, because we do not want the guide to slide off the slide system, because if this guide comes off the slide systems, all the bearings will come out of it. So when you're working with these, be careful, because if you lose the bearings from the guide that runs on the slide, okay, then it's going to be no good anymore. Okay? These do come packed in grease, so you may have to clean them out a little bit to get a nice smooth slide, all right, because as they get put into shipping, they can gum up. We just use a little bit of WD-40 or a little bit of oil solvent in there, and then you'll get a nice smoother slide, all right. So as I said, these will constrain the movement in one direction. When mounted, they're very, very sturdy, okay, and you won't get a slide. And we've just mounted this with our M3 socket head and cap screws, okay, right to the slide mount here. So this one has 2 250 millimeter slides on it. that you'll be looking at and going forward. So that's the one type of slide system that's in your collection, all right? And that's the type of slide system that we're going to use for our OMS. All right? The second type of system that you've got is the rack and pinion, all right? And I'll give you a little bit of an overview of the rack and pinion here. So I'll slip back over and then we'll talk a little bit about how to mount the rack and pinion and put the rack and pinion together. So a rack and pinion type of system, as it says here, it's a special gear arrangement that converts the rotary motion into linear motion. And the rotary motion will be supplied in our terms by our motor, either our DC motor or our servo motor. Both of those can work, all right? There is a circular gear, which is known as the pinion, that engages the teeth on a linear bar, all right? And that linear bar has teeth, so that's the rack. So you've got the pinion and you have the rack, and I'll show you that in a minute. As the teeth engage the rack with the pinion teeth, the rotational movement that's applied to the pinion will cause the rack to move relative to the motion, okay? So in other words, it translates the rotational motion of the pinion into the linear motion of the rack, all right? You get a rack and pinion supplied inside of the kit. Generally what happens is we mount the rack itself, okay, to the channel. So the large rack gets mounted to the channel. We're going to show you a couple of different examples here, but in your build, you are mounting your rack to channel, all right, on the system. So we'll show you that. You'll be able to see that as you go forward, all right. There's a rack bracket, which is a small piece that is usually also then mounted inside of a smaller piece of channel, okay. So if I look at my screen here, I have the rack, okay, and I have what I'm going to call the rack bracket right here that is mounted to a piece of channel. This provides a guide and allows it to slide along the rack, all right, as you go through. And then with the pinion gear, what happens is it's mounted in one of the mechanisms, and it allows you to translate the rotational motion to the linear motion going forward. All right. So here's one of the racks in the system. It's mounted onto the channel. I've got this one because it's a 288 rack mounted onto a 288 channel. In your build, you're going to mount this onto 334? 336. 336 channel. My math's off. James's math is good. All right. So you're just simply going to mount those onto the channel. If you take a look at it along the back side here, inside of the rack, there'll be brass inserts inside your rack. So this black piece that will allow you to center that and fasten it, and use M10 socket headed cap screws to mount the rack onto the channel, right? Once you've got the rack mounted onto the channel, the basics is that this pinion gear is what's going to translate that rotational motion, okay? So as a shaft, okay, turns along here, it translates the rotational motion on the rack and pinion. Couple of different methods and slides to do that. I'll just show you that I talked about putting the guides onto a smaller channel. So here's a system here that uses a servo motor, and I'll talk more about this later, okay, and the way that this one is mounted. Okay, and the guides are in the smaller channel, and the rack pinion gear is there. And when you mount the whole thing together, all right, and slide it on, right now because the motor is locked, I cannot move it. Okay, but basically as the motor moves, we translate that rotational motion, okay, into linear motion. All right, back and forth. So in this case, we use the two guide brackets. All right, we put them onto the smaller channel, and then the whole thing slides in. So I gave you a picture of that so that you can see it. There's another one here where we mounted the rack onto a flat channel, Okay, so this rack is mounted onto a flat piece of channel for a mechanism, right? But you can see that it's the same type of build system right here, okay? There's the guide, all right? It's mounted on the rack, and then inside the rack is that pinion gear that translates the rotational motion into the linear motion going forward. So simple rack and pinion designs that you can use in your robot system. All right. There are benefits and disadvantages to both. I actually had them in the presentation, and I did take them apart. Okay, some can be more sturdy than others. We can do some that are faster. Some will have a little bit more accuracy. Okay, this the rack and pinion that I had up was fairly sturdy, but if you get them too big and they're not tight, there can be a little play in rack and pinion, and that's just because there's in the gear system that's there's going to be a little play as you go forward. All right. When you go to mount the motors for this, you're going to use two different types of motor mounts in the design. So I thought I would talk about that. You will use the servo mount front plate that I'll talk about in a second. The standard size servo mount plate, it's got threaded holes on the end. So there are 4 threaded holes on the end, and it has through holes on the face. Okay. You're going to use the threaded holes to mount the servo frame across the servo motor, or off the front of the servo motor, as I'll call it, or the stickered side of the servo motor, okay, or the drive side of the servo motor. And this flat bracket will aid you in mounting the servo as well as providing support. The through holes are going to be used with standoffs or spacers. Okay, and this will allow you to mount this motor parallel to a flat surface. So I'm just going to flip back over again. Small screen. Yeah. So if we take a look at it, basically what happens is this is the motor, okay, here, and this is that standard front mount bracket. So the motor fits up through the front mount bracket, and then there are 4 socket-headed cap screws here that we can use to secure the motor to the bracket, all right? These are your through holes right here on this side. So what this does is it provides a firm mounting point for that motor, okay? And it also provides stability for the motor. So the motor doesn't twist, it has some bracket, because if we don't, what happens with this is that motor, when it's doing radial movement, okay, it can begin to torque and twist out of the system. To show you the sample of that, that's why I had these up here before. These were one that you know, we had a student in here trying to build, and what he did when he mounted these mechanisms, okay, was there's your servo motor, but he didn't use the frame, okay? He just used standoffs directly to try to get that distance, okay? Right here, he's got the servo to shaft adapter. He's got a couple of spacers so that there's no movement. And then he has the collar clamp, okay, here, mounted up to the bearing. And I'll talk about that in a little bit. But if you actually look at this from different angles this way, you'll see that these are beginning to twist, all right, inside of here, and you can actually see that these are beginning to be crooked, all right? This one gives you a much clearer angle at it, all right? If you look at it, you can see that these are beginning to twist out at an angle because there's not a lot of support for the torsion that's put onto that motor, okay? So the idea behind doing this is that you would use that bracket, okay, and put your standoffs and screw them through here, and that provides additional support to the servo motor. Right? So I just wanted to talk about that because in your assembly, you're going to see that this is one of the ways that we have put that together. All right. I can't find my... All right. You will also be using the 6mm D shaft to servo hub adapter. All right, so that's a small adapter. On one end, it has a 25 tooth spline, which is for your servo motor. So that'll go on here like this, and it'll press fit onto your servo. Okay, so that you can do that. Use the servo. And on the other end, it'll have a 6mm D shaft adapter. All right, and with that, that's where your shaft is going to go in, right? And there is a set screw point on there for you to put against the flat of the shaft adapter so that you can translate the motion, right? So you can use spacers in there as well, because you don't want any play this way at any time on movement, because that causes it to come loose, all right? And it'll add for some extra stress on the system. So that's why in a design like this, you would have seen that he used some spacers, okay? So that nothing moves apart in any direction, all right? So just a couple of ways for you to mount the motors on your system and a couple of tips and tricks for you. So when you do your builds, what's going to happen with this, and when we get into these, I'll talk a little bit more about it in a couple of sections here. There's a couple of tips for each part of the build that we will look at going forward, all right? We're going to use subassemblies. So basically when we have a subassembly, it's pretty standard. It's a collection of parts put together as one unit. And we broke our robot into 4 subassemblies. Right? The idea behind doing this is that these would be assembled first before the whole product is put together, right? What that does as a process is it makes it more efficient from a manufacturing standpoint, okay? When everything's done in a subassembly, you can simply assemble it more quickly. It's also going to help us reduce complexity of the robot, because everything's in a subsystem that can be looked at and tested. So when we build our robots and test them, as an example, and I'll show you on the next slide, we build the drive base first, we test, we work on the drive base, we work on our motor code and so on. For your World Skills team members, you know, that can be one team member working on that, or one part of a team if you have more of a team supporting you. We then take the rest of the assemblies and break those down into sub-assemblies, right? This also makes repairs easier, because we'll build separate extra small sub-assemblies, so that if we break a shaft or a motor or a belt or something, we don't have to replace the one part. We just quickly take the sub-assembly off and put the new previously tested sub-assembly back onto the robot, right? So you want to make sure you have spares. It also allows for a division of tasks, or what I call sharing. So if you have 2 competitors in World Skills, one can be working on subassembly A, one could be working on subassembly B. One could be working on the drive base if you're working on C-1 or C1 and assembling, let's say, if that's when it is, and getting the drive base onto the court, testing the drive, testing movement, and so on. Well, the other can be finishing subassemblies, all right? That way you don't have 2 people trying to get into that confined space and work at the same time. So for our sub-assemblies that we talked about, and we broke our training down into our sub-assemblies, and some of the training, you know, you may be able to build something a little bit faster, but we also broke it out this way to give you a good understanding of the time frame it requires to build and do each section, so that you know what's going to happen. So in our subassembly, we have the drive base. It's red on my slide because we built the drive base on Tuesday, and that should be set up and ready to go. We are then going to build the elevator, which is the first part of today. So when I'm done here, I'm going to make sure that everybody will take a break. We'll make sure that everybody has the 3D PDF files. You'll go through the parts list and you'll begin to build the 2 sections of your elevator, right? And I'll talk a little bit about that. You will then build what we call the A-frame, which is the main support structure for both the elevator, the OMS, and the electronic system. And then you'll build that object management system, or our gripper, right? So we did break it down into 4 complete sub-assemblies for this robot, right? the first thing you will build is the elevator. This is the parts list for the elevator. There's two 336U channel. We need 6 flange bearings, a few other parts going forward. It's fairly simple when you're going to do this. If you find that as you're building, we've used extra parts, that's great. But as an example, we can just build 1 elevator instead of 2. We're using a double slide rack and pinion system on this robot, much like what you would see on a forklift. Okay. So this is your parts list for your elevator. So there are a couple of points about working on the elevator that you can see in this slide that I'd like to discuss, and then I'll just go back and I'll show you some examples. So there's 2 pieces with the 334 and 2 rack on the 334. So you can see that on my slide right now, okay, with that section up, okay? And then with the slide elevator, there will be, okay, there's a question in the chat. Should everyone use Shanghai 2021 at Shanghai 2022? It is the same kit, okay? There will be no difference. Just remember that World Scales was pushed back 1 year. So it went from 2021 to 2022, that's all. Okay, but there were no hardware changes between the 2021 kit and the 2022. As I said a little while ago as well, that this competitor information document has not been released yet, okay? And we cannot comment on a competition that has not had the competitor information document released. So those questions will all be answered for you through your chief experts once that document is released, okay? What's that?
July.
Yeah, and that's it's coming up, but that's not something that James and I do. So you know, you could discuss that through your chief expert, and he can ask, and you'll get that information. All right, going forward. A couple of things about your assemblies that you're going to do here. You'll see that you're going to put a pulley on using the flange bearings, and you'll see that I have a collar clamp here using the flange bearings. You'll also see that we're using gears here, and the gears that we're going to use are also going to be mounted through the hubs, okay? So your 6mm hubs that come into the collection. So if I go back 1 slide here, okay, you'll see you'll have a 6mm shaft hub, okay? You'll have some 1mm spacers in the system, okay, that you're going to look at, and I'll talk about those, and you'll have a 10-tooth bolt pulley. All right. So I'm going to stop sharing, and we're going to just discuss this a little bit. Can we go back to this camera? All right. Okay. So it doesn't really matter what I grab here. I can grab anything. So you are going to be using the flange bearings here, okay? They're going to insert in the, and I'm going to use this 120-degree flat, okay? They are going to insert into the holes, and you'll notice that in my slide, I had some little red pieces that are spacers, okay? Now, so that you can see it, I've got a large spacer here. The key behind the spacers is that you're going to use 1mm spacers, right? On the top of these flange bearings or anywhere where we can get that metal-to-metal contact. So where we have metal-to-metal contact with the bearing, all right, and a shaft collar or anything else, we put in a spacer, right? And that's what you see on that diagram, and that's why they're there, all right? Because we do not want that metal-to-metal contact to damage the bearing, right? So we put the spacer there to provide support and to make sure that we get a nice smooth transition when we're using bearings. So I've overemphasized that, but that's the section that you're going to use, all right? The bearings pop in. It's the same thing if you're asked to use a bushing on one end, okay? The bushings pop in as well, and then the shafts can go through, right? Your collars themselves will also be there. You can use multiple shaft collars if you want, all right? So in this case, there's a small shaft collar on the inside. Just watch your set screws, okay? Always check your set screws. As part of your robot maintenance, for instance, after each time you do a run or work on your robot, you should check those set screws to make sure they're tight. As I said, we talked about blue Loctite on Tuesday. You could use blue Loctite, but if you're testing, you're going to take these apart and reassemble all the time. You might not want to use that blue Loctite till you get to the very end of your design, right? So that you can see it. And feel free to mess around and change the design. When you do the gears, there's going to be the 6mm shaft tub. Okay, so the shaft tub, if you look at it, it will have 4 holes in it that are threaded M3 to attach this to things like the gear, and then it will have 4 holes that are larger that are through holes. Okay, so if you had to put a bolt or something all the way through it. When you're going to attach the gears, okay, the gears have through holes on it, and when you're doing the shaft tub, okay, what you can do is you'll just simply put the shaft tub over, right, and you can run through the through hole on this side into the threaded hole this way, okay? Or if is what you want to do. So you go through the through hole and into the threaded hole, right? And you can attach that hub to the gear for the drive mechanism, right? You can do it this way, or you can try to do it this way. Just remember that if you try to do it this way on a gear, that you don't have access to that set screw that's on the inside of it, okay? So there's 2 set screws on a shaft hub, one for the flat and one for the other side. So just be wary of that design. Maybe you want to save space and mount it this way, but on our design, you'll notice in the picture that they're all put on this way, okay? And we've just gone through the through holes and threaded into it. So that's how those 2 mechanisms mount together so that you can drive the different gears. Did you want to talk about those gears? You're going to do it with the assembly, with the ratios, okay? All right, and during the assembly, I'm going to talk a little bit about the gear ratios, why we've used the certain gear ratios for each type of motor so that you can see it from that design standpoint, okay? So just a point on that elevator mechanism when you're going forward. All right, so there's your, like I said, the spacers there with the pulley, okay? 1mm spacer here with the shaft collar in your design. There's your flange bearing, okay, inside of your channel. And on this side here, there we are mounting the hubs, okay, to each of the gears. And when we mounted the hubs to each of the gears, you'll notice that we do not have in your bill of materials the actual fasteners, but I believe you mounted these with the button head, right? Yeah. Okay, and the reason he mounted those with these the button head screws was to get a little bit more clearance so that the bearings don't, or the socket heads don't stick out further, and you can mount those shafts a little bit tighter and closer together. All right, so I'll just go back and cover that one more time, because I bet the next one is for the A-frame anyways. Okay. So once again, go back. All right. So when we mounted these, it's a little hard to see. We used the button head. Okay. So as opposed to right. So as opposed to a regular socket-headed cap screw with the large end on it, okay, we used button heads, which are the small ones, so that we gain a little bit of space and a little bit of clearance. Because remember, these are going to be moving, right? They're rounded off. If they bump into anything because they shift a little bit, you won't run into that friction of them touching. So that's what we use through the through holes to mount those in. Okay. All right. So now I'm going to sit and assemble everything for you and adjust it. What we'd like you to do is to do the elevator, which basically consists of the 2 pieces of 334 channel, 336. I'm always 2 millimeters out in my life. Okay. It's the way that it is. So 2 pieces of the 336. Your racks are going to mount, and then there's a few other components for that mechanism. They will be in 2 separate pieces for now when you assemble them. Okay, so what we will do is we're going to take a 5-minute break right now. If anybody does not have access to the share, put your email in the chat and we'll add you to the share in that 5 minutes. Then we're going to come back and be live if we have any questions for your build. This is a fairly simple build, so we'll probably give you, let's say, until 10 after 8 to complete it, and then we'll go on and discuss the next subassembly, which is the A-frame. Okay, and there I've got one email right now, so we'll make sure that I add that to the share. Okay, so get your parts together. Good building. We'll be here. If there's any questions, raise your hand, put them in the chat, and then we can go through and answer the question and show you. All right, great. Have fun, everybody. All right, we're still here, and hopefully there's building. It seems pretty good when no one asks us questions, but a couple of points for you. I showed you how we use the button head screws to put the hub, the 6mm shaft hub, onto the gear. And explain to you the reason why, and that's the way that it is, I believe, in the documentation that we sent you. But a couple things, because we always can do design changes and so on. So we're just going to switch over to the robot side, camera 4 as we call it. Okay, so just a couple things here is it's a little hard to see, but I'll show you in a minute that on these gear systems that we put here, and this is the first one right along down here, okay, that you're gonna have onto the one side of the elevator, we actually doubled up on the shaft hubs, okay? So we put one shaft hub on this side of the gear and one shaft hub on the other side of the gear, okay? And to do that, we did actually use a 2mm spacer in here, and we used a 12mm socket-headed cap screw. Why did we do that? Because this is a critical component, all right? And it drives this mechanism, and it drives this mechanism with a DC motor, which is a fairly high torque motor at the 60-to-1 gear ratio that's on here, right? So we want to make sure that this does not slip or fail, so we have doubled up, okay, on the components here. And I'm just going to move our robot out of the way a little bit. So what we actually did with the gears, okay, was we took one gear, we took one shaft hub, we put the shaft hub through the reverse direction that I told you. We have another shaft hub, okay, on the outside of the gear. And then we actually threaded through the first shaft hub and through the hole a 12mm socket-headed cap screw. Okay, so that 12mm socket-headed cap screw, should pick one that we didn't use 50 million times. Okay, that has been threaded all the way through. Right. Goes through the through hole on the gear. And as it comes out the other side, we are going to thread that into another shaft hub, right? And what that does, and it's a little bit tricky because remember you're going from one thread through another, so you can get some offset in there, is it provides me double the strength, right, is what I want to do. It's up to you if you put one through one way or the other. If you want to have 4 set screws on and you have enough clearance in your design, okay, you could mount both shaft hubs on either side, all right? Am I saying that you need to do this? No, because remember that it may look like a small component to you right now, but every component that you add adds to the complexity, okay? So you could do it this way, or you could do it this way, right? It adds to the weight of the robot, okay, which may throw off your center of gravity. But if you think it's a critical part and you're worried about it, or if you may have a slippage or failure, then you can add 2 shaft hubs either that way or that way to provide more strength, okay, on a critical gearing system, all right? So we'll let you keep building, and I think we'll give you about, we're not gonna rush you on this, we'll give you about another 20 minutes to finish both sides of the elevator, all right? Okay, we're still here, so let us know. the picture?
No, rotate the robot.
Right. Oh, this robot weighs what, 150 kilos? No.
5.5.
5.5 kilos. How's that? No, let's go at a bit of an angle here, right? So remember, you're building the two structures here, right? Which are the sections for your elevator mechanism on that robot. Nice and close. There. Okay, everybody, hope the, what are we building? The elevator. The elevator is going good, and you've got your two pieces for your elevator. As I said earlier, we're not getting a lot of questions. We had a couple. Some stuff on the PDF files. Couple of points. Please remember that they're true PDF files, so you do need Adobe Acrobat to open them. And the reason is that they're coded for that 3D aspect. From SolidWorks, actually, which is what the CAD was designed on those. So take that PDF, download it locally, get Adobe Acrobat and open it. When you do that, make sure you trust the content. If you don't trust the content, you'll just get blank screens. You'll be able to see nothing but the normal non-interactive PDF outlines, okay? The other thing is, make sure you download them and then just be careful, because if you're like me, I'm challenged sometimes. I just double click on the PDF and it tries to open in my browser because I have a PDF add-on inside my browser. Because it's not true Acrobat, I see the outline, so I see the Studico Robotics logo, and I don't see anything else. So it does have to be true PDF. It's something new that we're trying for all our assemblies, is to take everything that we design and put them into that 3D PDF format. It will get better from our standpoint. We were just discussing today how we can arrange the parts list a little bit better so that it's easier to read, and a couple of other tricks and so on as we look at that. All right. So you should have the two separate pieces for your elevator, right? If I back this robot in, there'll be two different sides, right? One side here and one side here. The next part that we're going to talk about is what we call the A-frame. So the A-frame is what's going to support these two sections that you have sitting on their own right now with nothing in them. And it's basically this back portion here, all right? Looks pretty complex right now on this robot because all the wiring is on it, okay, from that standpoint. But there are, a couple of key points. You've got some shorter channel that you use on the A-frame, okay? You have a certain, I can't even get my finger around here. When I do this, the camera's backwards to me, so that's the difficulty. You have a bracket here that we'll talk about. You'll notice it's a little bit of a special bracket. It allows you to turn it at angles that we've used, okay? And this frame is what's gonna support the elevator mechanism, which is what's going to support the OMS on the front of the robot. Okay, so I'll talk a little bit about the A-frame right now. Let me just get back and I'll share my screen for you, and then we'll let you go on and build that A-frame. I just got tweeted. Isn't that cool? All right.
Oh, that's UPS.
Oh, wrong screen. You're looking at my UPS. Oh, that's terrible. I clicked on the wrong one. How's that? All right. Okay, so this is the A-frame bill of materials right here. It'll be in the document for you. I got a BILL. Look at that. Bill of materials. All right. There's two 144 millimeter U channels. You have your end piece plates in here, quantity 3 that we use to put the channel together. So the end piece plates are sort of like the motor mounts, but not like the motor mounts that we put in the other day. Okay, so they're going to go into the end of the channel so that you'll be able to put the channel together. You have some 48 millimeter U channel, some 288 millimeter U channel. We do have in this parts list right now the VMX robotics controller. I would build the frame. You can build it without it right now, or do you want him to put it on because it's easier to wire it?
Here, I'll switch the stop sharing.
Yeah, I'm going to stop sharing, and James just maybe wants you to do that. We're going to find out.
So the reason we have the VMX there is once you start building the top here, it will become harder to get your hands on the inside to actually screw in the VMX itself. As you can see, there's some screw holes here. And if you don't assemble it beforehand, you will regret it later, as with me, I have nice big hands. So
Sausage fingers.
Not sausage fingers. And I can't exactly get in there to hold the nuts when I'm screwing in the VMX. So it might be a good idea to put the VMX on before you install it fully.
All right. Okay. And there's a couple of other different things that you've got there that I'll talk about going forward. You'll notice that this mechanism uses the Maverick DC motor. Okay. So a couple of little things here. You are going to use the 76141 motor mount clamp kit that I'll show you in a minute. Okay. That clamp kit has both a top and a bottom. You'll see there's a picture of a mechanism there with a motor that is mounted in one of these mounts. It's a chain-driven mechanism. Don't get confused about that. It's just a picture that I had inserted in here. So you're not doing a chain-driven mechanism on this robot right now. Maybe one day we'll do one with chain-driven. Okay. Each one of the gears require the shaft hubs. So you'll see that we talked about that in the last build. And we talked about the fact that that gear has the 4 button head cap screws on it and 1 shaft hub. For now, you don't need to double up like I talked about earlier. That was just a little bit of a tip and a tip and trick, okay, going forward with that. So I'm just going to switch the screens up for a minute.
You're so sure.
And stop sharing. I don't really have okay. So you're going to use that that 2-piece motor mount. There it is right now, broken out. Okay, so that you can see that. If you have it in 2 pieces, it comes like this. So it's a 37 millimeter motor mount for the 37 millimeter motor. Okay, because that's what the width is of the motor. You'll put those in that top mount and you can hold it as you go forward. You're just going to slide the motor in. So you use this motor mount. This particular motor, if you don't want it to twist, you could actually put a couple of screws through here, longer socket-headed cap screws to put a little tension on the motor. I don't think you're going to need to do that for what you're going to do. It's pretty good this way. And I don't think it's in the design anyways, what you're going to do it. So that's just that motor mount. Like I said, it comes in 2 pieces. All right. And you're just going to put that on. So that's one of the newer things that you're going to use. And this is going to be used to mount that 60-to-1 DC motor for the A-frame, which is what we're going to use to drive the elevator up and down. Now, did you want to talk about your gear ratios right now?
No, we can show it, yeah.
Okay. All right. So I'll let James just show that. It's just going to talk a little bit about what we're doing there and those gear ratios.
So one of the main reasons why we also use this mount is that if you know anything about gears, you have a gear pitch, and on our channel, you can't have 2 of the 64 tooth gears right next to each other in the same holes. So you need to offset it a little bit. And by using this mount, we can rotate the motor, which has this gear attached to it, that it then meshes correctly with this gear on the elevator so that we could drive the output shaft. That's one of the benefits of having the offset shaft with the spur gear, and that's that we can rotate it inside that motor shaft and to put it here. So right now we have a 2-to-1 ratio. So 2 rotations of the output shaft is 1 rotation of the motor shaft. And the reason we have this is we want to speed up our elevator because we don't need as much torque as what the motor has to lift the actual object management system. So we can gear it down to make it faster. However, if you were using a servo, for example, the current servos we have are 25 kilograms per centimeter on the output shaft. So you might need to gear it up instead of gearing down to allow you to lift the object management system if you're using a servo.
Okay. All right. So just a little bit of tips back and forth. And, you know, we could put a lot of different motors and a lot of different servos in here. But one of the things that we tried to do, and you'll see this going forward, is just to streamline it a little bit so that there's not as many components for you to think about, and not as many different types of components for you to have to buy. So that's always a concern. So just a little bit of a talk about those gear ratios going forward, okay, and mounting everything up. All right. So like I said, there it is, all mounted. It's got the hub on it, and it's a good picture for you to see going forward. All right. So this is the actual CAD file so that you can see it. So you're going to build that A-frame. It's pretty straightforward what you're going to do. It's easy to see if you rotate it around and look at it going forward. I do not have the fasteners, okay, on that CAD because it would get a little bit too complex to put each fastener in. So just remember, you're going to use your 12 millimeter socket headed cap screws and use your KEP nuts for this, as opposed to what we talked about with the nylock nuts, because I'm going to assume that you wish to disassemble it as you go forward. So you're just going to build that frame subassembly. On the right here, you'll see there is my motor, okay, mounted in the motor mount. All right, and then I've got the gear mounted to the end of the motor. All right, just so that you could have a look at that and see it. Okay. All right, so that is the A-frame. We can go ahead and we can build the A-frame right now for you. I've got 8:28 or 8:30. Why don't you all take a rest break, or you can take rest breaks whenever you want. We're going to be here to answer your questions on that, okay? And probably we'll give you about a half an hour to put that together. And at 9 o'clock, we'll go back and we'll talk about the difficult piece of the build, which is the actual OMS, and then the complete assembly for the OMS. All right, have fun, everybody. I'm always ready. I put my glasses on because I couldn't see anything, and the whole world is bright and cheery again. Okay, so hopefully you've been building. We're not getting a lot of questions, so you're either all just taping this and doing something else, or you're actually busy building, which is good. We're going to get a little bit more interactive here. We're going to talk about the object management system, or the OMS portion. And you'll notice that on the robot that we had up here, our OMS is not actually on the robot. So James is going to go through that part of the assembly because it's a little more difficult and setting everything up for that system. All right. I'll take you through the parts list and a couple of other things. Okay. So for your object management system, there's the bill of materials that comes off of your 3D integrated PDF. Okay, so we need a couple of things you haven't had before on here: the 10-tooth pulley belt, some different spacers, the 5 millimeter spacer. You'll notice that in order to get that 2-to-1 gear ratio, or are you going 1-to-2? Sorry, 2-to-1 you're going, right? Our gear ratio, we have using our 32-tooth gear and our 64-tooth gear in here. And we're just going to add a D shaft onto this subassembly. Right? So just a couple of points about this. This is the OMS that's broken down. We jazzed ours up a little bit. We used some extra rack and we use an extra slide. All right. And this is just because of weight load and some of the types of things that we're trying to do. As I said, it is just an example. So some of you that have more than one kit, you're going to have this extra slide that you can add in for this build. You don't have to. You can redesign the build. As I said, our idea here was to build one mechanism that used the DC motor and one mechanism that used the servo motor. All right. Remember that when we did our last elevator, we did our 3-hour session on the elevator, we actually used one 250mm linear slide and one servo motor. You could actually build some sort of mechanism like that if you wanted to as well, and put that across the top. But we're just trying to be a little bit more complex when you're doing it, and to give a little bit more support. Okay, this system is going to use a belt drive, okay, to drive it. So there's a couple of things. Essentially, it's a small conveyor system. We're going to use a timing belt and drive it with the motor, the rotary motor, which is the servo. We're going to loop the belt around one of the pulleys. We're using a pulley on both ends, I think, James, or are you using an idler on one end? I'm not sure. So he's going to use the idler on one end
That's on the elevator.
Of the travel. So the idler that's on the elevator. Okay. So yeah, I did actually watch the instructions and wrote this correct. Okay. One of the things about the belt drive operation is that you need to have the correct tension. So you must have a method to adjust the tension of your design, not if your design. I apologize for that. As the belts wear, they can stretch and they can lose tension. And if there's not enough tension, the belt will slip on the timing belt and you could get lost motion. So if this is a critical mechanism, please remember that. You got to have a way to either adjust the tension on your belt, okay, or you want to make sure you have spare belts and systems ready to go when you're going to work through that. All right. And I think James's mechanism, he's built some form of tensioner into here. I actually like it, James. That's pretty good. I can see it. So he's very, very creative as we go forward. So I will back that off now, and I'll let James talk about the OMS and how it's put together. Do you need me to adjust that camera a little bit? Just let me know. Okay.
Stop sharing.
I have stopped sharing. So if you want it to come up a little, let me know.
So before we attach to the robot, there are two arms that use to clamp the ball. They will act as a differential. So essentially we'll use a pinion gear attached to a servo. That when rotated will come in, when rotated the other way, we'll push them apart. Each one of these arms has one rack and pinion on it, along with some channels and brackets. There are two 3D printed parts on this. You don't need to do that. You can use spacers for this 3D printed part, which is 9mm. That's just to space the plate from the rack and pinion, that when it attaches to the linear slide, which is here, that it can screw into the top better. This 3D printed part here is just used that it can cup the golf balls a lot easier and stack them when required. As this one can hold up to 3 balls when picking it up. Of course, you could take this off and design a different type of system if you wanted to when clamping, or you can design it that it goes down like that if you wanted to. This unit here in your CAD is the 288 low profile channel. On here, I have the linear slide. This provides stability to the differential. I will show why we have that in a second. On this, I have 2 slides. However, in your kit, you only have 1 slide. So you can choose to put one, or you can add another one and lose penalty points. It's up to you. But but I have two just to show for the training robot and different concepts for training purposes. So let's look at the robot. The robot here, we have a flat plate that attaches to the two 48mm channels on the elevator. I'm not sure how well you can see that. So I'm going to tilt it. There you go. So we have the two 48 channels that have the rack and pinion glides on it. There is no pinion gear, as the elevator is not driven by a pinion gear. It's driven by that DC motor and the belt drive, which is here. And here you can see I created a little tensioner which pushes out to provide tension to the belt. Sorry, it's our one coffee machine is going off right now. Okay. Here we have the servo motor, which will drive the pinion gear for the differential. I put some 5mm standoffs here to push the servo away from the plate. This allows, if you can see down there, for the shaft adapter to be pulled away from the front plate and allow for a bushing to be put in. So if you look here, there are two glides, one for the top and one for the bottom, and they'll both attach to this pinion gear, and then when you slide, it will slide as well. I'm going to move this camera out of the way and then tilt the other one down so that you guys can see me assemble this robot better. Sorry, I was muted. I'll go over it again. So we have the slide mechanism here. Once attached. So there are some screws here which hold the main slide plate to the flat plate. You want to make sure that they're tightened properly in a star pattern. This is to create an even torque amongst them. My screws were a bit loose. Now, the reason why we have the slide on the 288 channel is there is a lot of play here. And with the slide, it will add stability to the arm and allow the arm to move smoother in the proper direction. The slide mechanism lines up perfectly that the 2 inside holes here on the slide will screw into the holes on the L bracket. So I'm just going to line this up. So I'm just looking for the screws that I used for that. So that is now screwed in, and you can see how much more stable the arm is. I'm shaking it, and it's moving the whole carriage. So that shows that this is now in properly. And when it's moving, it won't have the shaking, as you can see here. As you can see, it's very stable now. Loose, stable. That's what adding the linear slide does. Now I'm going to screw in the bottom linear slide into this one. Push them in a bit. So to get underneath here and see properly, I'm actually going to tilt the robot on its side. And as I have the battery in here, I'm going to take it out so it doesn't fall out. Hard to get the bottom line.
You moved it already.
Well, I'm using that one.
Oh,
I
perfect.
can see better.
Perfect. Your robot fell over.
Yeah, because I have to screw in something from the bottom and you can't see easily.
Better post that 3D printed file.
Once that's screwed in, I'm gonna go grab it. Should be there by the on the left. On the left. So now when we look at the clock, turn it around, you can see that we can close it. and it will get nice and closed. And then when the servo opens, it can get nice and big. So here we have some of the objects from the Waste Management Challenge, from the previous World Skills. We like to use round objects a lot. What I'm going to do is you can close the claw, and you can see how well it holds the ball in place. You can see I can even have another one in there. And like I said, it can hold 3 pretty easily. So with the elevator plus the claw, we'll be able to go to the ground, pick up a ball, bring it up, and deploy it to where we need to. Now, besides the sensors and everything else on the robot, that is the training robot that we will be building. Next week, we'll be going over adding the electronics and wiring of the robot so that we can eventually start programming it and moving it around. If there are any questions that anyone would like to ask me or Derek, now is a good time to do so. Otherwise than that, we're going to end it for the day.
Well, we'll stay live in case there's any other questions, right? And we'll do a quick summary just before 10 o'clock. All right. So we will be here and all ready to go.
Hello, everyone. This is Frank Nanfera. I don't have video right now, but I notice everyone is still on, and I just wanted to openly speak about what everyone is going to receive in Shanghai. There was a question about whether the Shanghai collection that everyone's working on now or receiving now will be used in Shanghai, and the answer is yes. We went over this before. Some of you may have not heard or may have not read, but we're hopefully everyone will understand that everyone, you will not be working on a robot and bringing that robot to Shanghai with you. You will receive a robot on C-1. You'll get a full collection, assembled collection, and you're going to have to build your robot from scratch. Everyone will receive the exact same thing. The only parts you're going to be able to bring, and this is going to be explained further after we release the Shanghai Challenge on July the 6th, and we do a Zoom webinar on July the 20th. But this is all going to be explained then, but you will be able to bring wire management. So it's going to be some wires, some, how you assemble the wires and make it neat, etc. Wire management basically. And you'll also be able to bring some completed 3D printed or laser cut plastic materials. And there's going to be a certain amount that is, that you will be able to bring. It's not going to be, that you're going to have your own 3D printer there and you're going to have any amount of parts. The parts will be based on size and weight, and we're going to make that information available July 6th and July 20th, more information. So if anybody has more information, we're happy to provide that, but we will provide full details on July 6th and July 20th when we release the Shanghai Challenge. So if some of you haven't heard this already, we are releasing the Shanghai Challenge basically about 15 months early from the Shanghai, compared to in the past where it's only been 8 or 9 months previously. Now this is going to be about 15 months. The whole point of that was to give everyone plenty of time to work on their robot, to get ready for the Shanghai, competition, and also, the idea is to help to allow you to make the Shanghai Challenge part of your regional, school, and national competitions, so that you can start working on this and select the very best team that will represent your country in Shanghai in October. So with all that said, the robot is looking good. I think this has been a good practice. I hope that you're all enjoying this. We're certainly open to ideas of or suggestions of future training sessions, but we certainly hope that you're all learning something from this. Thank you very much.
All right, everybody. Derek has to mute because he was watching a Raspberry Pi video. Not a lot of questions, so hopefully everybody is building and getting the robot put together. So we'll just summarize. So what we've done so far is we built a robot base. We have 3 DC drive motors with it. We then built some sub-assemblies on the robot. So we have an elevator, we have a frame to hold the elevator and to balance that, okay? And we have the object management system on the robot, right? Those components, what we're going to do on Tuesday is take you through the wiring of the robot, okay? And probably on Tuesday, what we're also going to do is, because there's been some confusion, is we are going to go back to installing the programming software and all of the software libraries required from scratch, and setting up a program from scratch towards the end of Tuesday as we get everything wired together. All right. So we'll mount the Titan, we'll mount the VMX, okay, the ADC, the Servo stuff, everything that we need, we're going to mount up, and we're going to do some wiring. We'll have a schematic ready for you on Tuesday as a basic training robot. As I said, if you don't get a complete double mechanism on here, the idea is to build something that uses the DC motor to slide. So if you just get one elevator on a robot, that's fine, as long as we've got that DC motor and it's geared, and we can talk about the gearing so that you get used to using the rack and pinion. And also, as long as you've got a slide, a simple slide that uses the servo motors, that's entirely up to you. You could take the elevator that we built the last time that's on the Studica YouTube channel, you could mount it sideways, all right? You just want something so that when we code it, you can see how all of the mechanisms go together, right, in one robot. So we'll do that on Tuesday, and then next Thursday, we're gonna finish the complete project and all of the coding for this, all right? We are recording and then we'll edit, and once all of the sessions are done and we've edited everything, we're gonna post this series to the YouTube channel for everybody to work, okay? So thank you for participating today. We got here pretty early this morning. It was a long drive in today. Any questions, we will stay online for a while. We'll keep everything active. And of course, you can always just send us a note if you have a particular question about the robot build or you're having any difficulty putting something together, and we'll answer those for you. So, get your base done, get a lift done, get something done with the servo, because the wiring is technically going to be the same. And we will see everybody again bright and early on Tuesday morning. So thank you, and we'll stay online here a little bit in case there's any questions.